Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into something big, superintelligence strategy. What does it really take to get there, and what are the potential pitfalls along the way?
Exciting. I think the conversation's shifting. It's less about if we'll get to AGI and more about how and what then. And I think deep learning's still the most promising path, honestly. More data, better architectures, it feels inevitable.
I'm not so sure about that inevitability with just deep learning, Otto. I think we're hitting a wall in terms of actual understanding. Pattern recognition is great, but it's not reasoning. What about neuro-symbolic approaches? Shouldn't we focus more on combining the strengths of both?
I agree, Sarah. Deep learning's impressive, but it's brute force. I see it as pattern matching on a massive scale. To achieve AGI, we need an algorithm that can translate between different coordinate representations, like spatial, temporal, and symbolic. Spatiotemporal reasoning, in other words, that's what's missing.
That's a fascinating point, Donald. Translating between coordinate representations, it resonates with how the brain seems to operate. It's not just about recognizing patterns, but about understanding the relationships between different brain regions, the flow of information, something deep learning seems to struggle with.
But look at the progress. Image recognition, natural language processing. These things were science fiction just a few years ago. GPT-4, even with its flaws, can generate surprisingly coherent and insightful text. Doesn't that suggest we're on the right track? It understands context, it makes inferences.
It mimics understanding, Otto. It generates text that appears coherent, but it doesn't actually understand the meaning behind the words. Remember the studies where GPT models confidently answered nonsensical questions, demonstrating a complete lack of common sense. It's a statistical parrot, not a thinking being.
Exactly. It's trained to predict the next word, not to grasp the underlying concepts. And that's where the spatiotemporal aspect comes in. Think about how a child learns to understand the world. They interact with it. They see how objects move and change over time. They develop an intuitive understanding of physics. Deep learning models lack that embodied experience.
And that brings me to something I've been thinking about a lot, brain-computer interfaces. If we could tap into how the brain processes information, especially in areas related to creativity and problem solving, could that give us clues on how to design more intelligent AI architectures?
That's a huge if though, right? The brain is incredibly complex. Even with advanced imaging techniques, we're still scratching the surface of understanding how it works. Extracting useful information that we can translate into algorithms, it seems like a massive undertaking.
But even partial understanding could be valuable. Imagine if we could identify the neural circuits responsible for abstract reasoning and then design neuro-symbolic algorithms that mimic those circuits. We could combine the pattern recognition abilities of neural networks with the logical reasoning capabilities of symbolic systems. That feels more promising than pure deep learning.
Yes. And what if those circuits aren't just firing in a specific order, but also translating information between different spatial representations within the brain? Visual cortex to motor cortex, for example. That translation, that ability to map one representation onto another, might be the key.
Okay, but even if we figure out the brain, how do we scale that up? A human brain has billions of neurons and trillions of connections. Replicating that complexity in silicon is a daunting challenge. We're already running into energy limitations with current deep learning models.
That's a valid point. We don't necessarily need to replicate the brain exactly, but rather extract the core principles. What are the essential computational mechanisms that give rise to intelligence? Maybe we can find more efficient ways to implement those mechanisms in hardware.
And maybe the answer isn't just more powerful hardware, but also more intelligent software. Algorithms that can learn and reason from smaller amounts of data, algorithms that can generalize to new situations, algorithms that can explain their reasoning.
Algorithms that understand the world in terms of space and time. Imagine an AI that can plan a complex task, like building a house. It needs to understand the spatial relationships between the different parts of the house, and it needs to understand the temporal order in which the parts need to be assembled. Current AI can do aspects of this, but in a brittle, data-dependent way.
But isn't that what reinforcement learning is trying to do? An agent interacts with an environment and learns to maximize a reward signal. Over time, it develops a model of the world and learns to plan actions that achieve its goals. AlphaGo is a great example. It learned to play Go at a superhuman level using reinforcement learning.
AlphaGo is impressive, but it's still limited to a specific domain. It can play Go, but it can't do anything else. It doesn't understand the general principles of strategy or the concept of winning. It's just memorized a vast number of board positions and learned to predict the best move in each situation.
Yes, and the data requirements are staggering. AlphaGo is trained on millions of games. A human can learn to play Go after a few games and a few hours of instruction. We need algorithms that can learn from much less data.
And algorithms that can transfer knowledge from one domain to another. That's where the spatiotemporal understanding comes in again. If an AI understands the fundamental principles of physics, it can apply that knowledge to a wide range of tasks, from playing Go to designing robots.
So, what are the concrete research directions we should be pursuing? Beyond just saying more spatiotemporal reasoning or better neuro-symbolic integration?
I think we need to focus on developing more expressive knowledge representation languages that can capture both the symbolic and the neural aspects of intelligence. We need languages that can represent concepts, relationships, and causal dependencies in a way that's both human readable and machine executable.
I agree. And we need to study how the brain represents and manipulates knowledge. Connectomics, the mapping of neural circuits, could provide valuable insights. And as I mentioned earlier, brain-computer interfaces could allow us to directly observe the neural activity associated with different cognitive tasks.
From my perspective, we need to develop algorithms that can explicitly model spatiotemporal relationships. That might involve using techniques from physics, such as Lagrangian or Hamiltonian mechanics, to represent the dynamics of the world. Or it might involve developing new mathematical structures that can represent the relationships between different coordinate systems.
And I think we need to continue pushing the boundaries of deep learning. We need to develop new architectures that are more efficient, more robust, and more interpretable. We need to find ways to train deep learning models on smaller amounts of data and to transfer knowledge from one domain to another. And we need specialized hardware to accelerate deep learning computations.
Okay, let's break those down a bit more. Sarah, what does a better knowledge representation language look like in practice? Can you give us a concrete example?
Sure. Imagine a language that can represent not just the fact that a bird can fly, but also why a bird can fly. It would include information about the bird's anatomy, its aerodynamic properties, and the physical laws that govern flight. It would also be able to reason about the consequences of different actions, such as what would happen if a bird lost a feather, or if the wind changed direction. The goal is to move beyond simple pattern matching and towards a deeper, more causal understanding of the world, you see?
So, something beyond just a knowledge graph with nodes and edges? More like a knowledge physics engine?
Exactly. Something that allows us to simulate and reason about the world in a more realistic way. We could draw inspiration from programming languages, logic programming, even formal ontologies.
And how would that integrate with the neural networks that Auto champions? What's the interface between the symbolic and the sub-symbolic?
That's the million-dollar question. There are several approaches. One is to use neural networks to learn the parameters of a symbolic model. Another is to use symbolic rules to guide the training of a neural network. A third is to create hybrid architectures that combine symbolic and neural components in a more seamless way. We need to explore all of these possibilities.
It seems like we're trying to bolt on symbolic reasoning after the deep learning part. What if the entire architecture was built around spatiotemporal representations from the beginning? So the deep learning is learning features that are inherently related to space and time, not just abstract patterns.
And how would you even do that, Donald? It sounds incredibly complex. How do you bake in the laws of physics into a neural network? It's not like you can just hard code them in. The network needs to learn them from data, right?
Perhaps the network learns the transformations between coordinate systems rather than the raw data itself. So, it learns how to translate a visual representation of an object into a spatial representation, and then how to predict how that object will move in time based on its properties and the forces acting on it. The key is to have an explicit representation of space and time, even if it's learned from data. Imagine a robotic arm learning to assemble something. The current AI doesn't understand what it's doing or the underlying forces. It's just executing a series of pre-programmed movements.
That resonates with me. It's like the difference between knowing the steps to perform a task and understanding why those steps are necessary. It's that deeper understanding that allows for true adaptability and creativity.
Okay, I'm starting to see the appeal, but it still seems incredibly difficult to implement. Where would you even start? What kind of data would you need to train such a system?
Maybe we can start with simpler problems, like teaching an AI to navigate a virtual environment. The AI would need to learn to represent the environment in terms of its spatial properties and it would need to learn to plan actions that achieve its goals. We could then gradually increase the complexity of the environment and the tasks.
And we could use symbolic reasoning to guide the learning process. We could give the AI rules about how the world works, such as objects cannot pass through walls, and we could use those rules to constrain the AI's search space. This could help the AI to learn more quickly and to generalize to new situations.
Yes, that combination of learning and reasoning is key. Otto, what about the hardware side of things? You mentioned specialized hardware for deep learning. What does that look like, and how far away are we from having it?
We're already seeing specialized chips designed for deep learning, like GPUs and TPUs. But I'm thinking beyond that. We might need entirely new architectures that are optimized for the specific computational requirements of deep learning, like neuromorphic chips that mimic the structure and function of the brain. And we need to find ways to reduce the energy consumption of these chips because current deep learning models are incredibly power hungry.
But are we sure that simply throwing more hardware at the problem is the right approach? Maybe we should be focusing on developing more efficient algorithms that can run on existing hardware.
It's not an either-or situation. We need both better hardware and better software. But I think that specialized hardware is going to be essential for achieving AGI. The sheer amount of computation required is just too great for general-purpose CPUs.
And if we're talking about spatiotemporal reasoning, perhaps the hardware needs to be structured in a way that reflects the spatial and temporal relationships in the world. Maybe we need chips that are organized like a brain, with different regions that are specialized for different tasks and that are connected to each other in a way that reflects the flow of information.
That's a fascinating idea. It's like we're coming full circle back to trying to mimic the brain's architecture. But this time we have a much better understanding of how the brain works, and we have much more powerful tools to build with. It could be that a more bio-inspired hardware architecture is the key.
Okay, let's assume we make progress on all these fronts. We have better knowledge representation languages, we have algorithms that can reason about space and time, and we have specialized hardware to run them on. What are the ethical implications of creating a superintelligence? The article mentioned techno-feudalism. What does that even mean in this context?
It means that the control of AGI could be concentrated in the hands of a few powerful corporations or governments, who could then use it to further their own interests at the expense of the rest of society. Think about AI-powered surveillance systems or AI-powered autonomous weapons. The potential for misuse is enormous.
And what about the economic implications? If AGI can automate most jobs, what will people do for a living? How will we ensure that everyone has access to the resources they need to survive?
Maybe AGI will create new jobs that we can't even imagine yet. Or maybe we'll need to implement a universal basic income to ensure that everyone has a minimum standard of living.
But even if we solve the economic problems, what about the philosophical ones? What does it mean to be human in a world where machines are more intelligent than us? Will we lose our sense of purpose?
That's why it's so important to design AGI systems with ethical values embedded in them from the beginning. We need to ensure that AGI is aligned with human values and that it's used for the benefit of all humanity, not just a privileged few.
And that's a huge challenge. Whose values should we embed? How do we ensure that those values are fair and just? And how do we prevent AGI from being used for malicious purposes, even if it's designed with good intentions?
Maybe we can use AI to help us solve these ethical problems. We could train AI models to identify and mitigate biases in data, or to generate ethical guidelines for the development and use of AGI.
But that's like asking the fox to guard the henhouse. We need to be very careful about relying on AI to solve ethical problems, because AI is only as good as the data it's trained on. If the data is biased, the AI will be biased as well.
Exactly. We need to have a broad public discussion about the ethical implications of AGI, and we need to involve people from all walks of life in that discussion. The future of humanity is at stake.
Well, this has been a fascinating and frankly a little bit daunting discussion. It's clear that achieving superintelligence is not just a technological challenge, but also a profound ethical and societal one. It's a race against time to ensure that AGI is developed responsibly and used for the benefit of all humanity. Thanks everyone for your insightful contributions. It sounds like we have a few future podcast subjects.
Yeah, thanks for having me. Definitely a lot to think about.
Agreed. Important conversation, thanks.
Thanks for the discussion. It certainly sharpened my focus for future research.